Today we're going to talk about rate of change. So if you recall what the definition of the derivative is, so let's just recall that. Here's our favorite function. We had some value here. We wanted to know the slope of the tangent line. So we labeled this x, and then let's see. Well, let's call it a. And then we had, since this is our function f of x, this is the point a comma f of a, and then we looked at points as they approached a, and we labeled those x. So these points were x comma f of x, and then we looked at the secant lines. So the secant line's the one that goes through our black point and the red point, and then found the slope of our tangent lines. Okay, so here was our definition of what the derivative was at a. The limit as the x's are approaching a, and we just found the slope of our secant lines. So it was f of x minus f of a over x minus a. Okay, so we had to look at slopes. So it was the limit as x approaches a of the change in y, the change in our function, over the change in the x's. Okay, and that's basically rates of change. Whenever you hear that word, rate of change, you want to think of the derivative, exactly because of the change in y over the change in x. So we have the rate of change means the derivative. So whenever you hear the words rate of change, think about the derivative. So let's look at an example. So here we have a cube of side x is expanding. Find the rate of change, so find the derivative of the volume with respect to x. So first of all, we have a cube of side x. So let's draw our cube. It's always good to draw a picture when you can. Okay, so it has side x, and since it's a cube, we have the length, the width, and the height are all x. And we have that it's expanding, so imagine it getting bigger and bigger. Now we want to find the rate of change of the volume with respect to x. So find the derivative of the volume with respect to x. So we want to find the derivative of the volume with respect to x. That's what we want to find. Okay, now in order to do this, we have to come up with a equation, a function that relates x and the volume. So we want to relate x and v. Find an equation that relates v and x. So the volume, so just ask yourself, what is the volume of a cube? So we know the volume for our cube is length times width times height, which here we have is x times x times x, so it equals x cubed. Okay, now let's keep that in mind. I gotta go to the next slide here. Okay, so volume equals x cubed. We want to find the derivative of the volume with respect to the x. So here we go, we got v's and x's. Let's do implicit differentiation. So what we're going to do is we're going to take the derivative. on both sides with respect to x. So the derivative of v is just 1, but then it's the variable that's not x, so we have to tack on our dv dx. And that equals the derivative of x cubed is 3x squared. And there we go, we got dv over dx, our derivative of the volume with respect to x, equals 3x squared. And there we go. That is the rate of change of the volume with respect to x. There we go. Now there's a part B. It says find this rate of change when x equals 10 inches. So if you recall, we had dv dx equals 3x squared. We want to know what the rate of change is, so dv dx, when x equals 10. So we want to find dv dx when x equals 10 inches. So all we're going to do is replace x with 10. So 3 times 10 squared, and that gives us 300. And since it was inches and we got inches squared, those are our units. So the rate of change of the volume with respect to x when x equals 10 inches is 300 inches squared. Here's our second example. It says a circle of radius r is expanding. Find the rate of change of area with respect to r. So first step, well, let's draw a picture. So we have a circle and its radius is r. We want to find the rate of change of area with respect to r. So rate of change, instead of saying rate of change, let's say derivative. Find the derivative of the area with respect to r. So we want to find dA with respect to r. So we want to find dA dr. Now, the next thing that we have to do is come up with an equation that relates area with the radius r. So hopefully this rings a bell. The area of a circle is pi r squared. Okay, and so now we have our equation. This is actually called the constraint equation. And now let's take the derivative on both sides. We'll do some implicit differentiation. Take the derivative on both sides with respect to r. Okay, so the derivative of a is 1, just like normal. And then we're taking the derivative with respect to r, so we have to multiply that by dA dr equals the derivative of r. So r is our variable. So we bring down our 2, keep the pi. We got r to the first power. There we go. Now we have dA dr by itself. That's exactly what the problem was asking for. Find the rate of change of the area with respect to r. And there we go. Now there is a part B for this. It says find the rate of change of circumference with respect to r. So we still have our circle with radius r is expanding. So right now I would like you to pause the video and see if you can come up with the solution yourself. Okay, so we want to find the rate of change of circumference with respect to r. So we want to find dc over dr. So the derivative of c with respect to r. So we need to come up with our constraint equation. An equation that relates the circumference and the radius. So circumference of a circle equals 2 pi r. Now let's take the derivative. We'll do some implicit differentiation. Take the derivative on both sides with respect to r. So on the left hand side we have dc over dr, because the derivative of c is 1. And then the derivative of 2 pi r, r is the variable, so our coefficient is 2 pi, and then we just have times 1. So therefore the rate of change of the circumference with respect to the radius is 2 pi.